Are you hearing me? Yep, oh, good. We're so lucky to have our colleague Stewart Prager back in Madison. For those of you who are age challenged, that is, you don't have as many years on you as some of us, you may not know Stewart, but Stewart was a faculty member here and spent most of his career, scientific career, leading the MST project and then moved to Princeton, where he was the director of the Princeton Plasma Physics Lab and has spent the last decade or so there. And he could give about 10 great colloquia, I'm sure, on scientific topics, but today he's going to talk about something that he cares deeply about, which is nuclear arms control. And I think I'll just give it to Stewart.
Okay, thank you, Carrie. Can everybody hear me? I don't know. Can you hear me? And then the next question I have is, since I'm like, I don't know, 40 feet from the nearest person, is it okay if I take my mask off, or people feel?
No.
It's okay? All right, I think it's not sacrificing anything since it's so far away. So I'll do that unless anybody objects. I'm happy to put it back on. Okay, anyway, first it's great to be back here. Obviously, I spent 31 years in the department, so I view this department as my physics home and Madison as my real home psychologically, even though I don't live here at the moment. So it's a real pleasure to be back and see how well everybody is doing here. Today I'm going to talk about nuclear weapons. So this is not going to be really a physics talk, but I think it's a talk about a topic that is probably of interest to physicists, should be to everybody. So I'm going to talk about the increasing peril from nuclear arms and how physicists can help reduce the threat. There's a bit of a trigger for this colloquium. We started an organization called the Physicists Coalition for Nuclear Threat Reduction, which is funded and sponsored by the American Physical Society, APS. So there's a group of 13 of us that are going around and giving these kinds of colloquia. And then also, don't want to do it during the colloquia, but if you're interested in talking about this more or learning about this coalition, which so far has 600 physicists in the US signed up for, maybe we can break after the colloquium, and anybody who wants to remain, we can talk specifically about this colloquium. I should say that any opinions I give don't represent the APS, only are my opinions only. So what's the motivation for this colloquium is that the nuclear arms threat is as extreme as it ever has been. I mean, it's just a very strange and hard to understand fact that we live in a world where a couple of guys can decide to kill everyone in the world literally in minutes, by pushing buttons. That's the world we live in. At this moment, single person or a few people can make that decision, and in 10 minutes, everything could be gone. The situation isn't a stable one. It's an unstable one, and it's getting worse. But the threat can be reduced. It's currently off the radar of the public because it's an invisible threat. Lots of reasons the public isn't paying attention to it, understandable reasons. But we think that the physics community can play a special role in advancing threat reduction because we have a special relationship to this problem. So what I'm going to do today is just review things. I won't talk about anything original, and I hate to say it, but I'm going to just review some technical aspects, the current critical situation, why it's a current crisis, some of the policy aspects, and then what the physics community can do. I'll make a mention of this Physicists Coalition, and then we can discuss afterwards if anybody's interested. So let me just begin with some well-known facts. It begins with the enormous power of the fission chain reaction. So here's a cartoon where you see a neutron comes in and bombards a U-235 uranium nucleus. It excites it, it fissions into two fission products, and it also gives rise to, in this cartoon, 3 neutrons. You get an amplification in the number of neutrons, and you get energy. The kinetic energy of the products is about 200 MeV. Kinetic energy of the incoming neutron is typically maybe 2 MeV. Well, this is one energy amplifying reaction. If you have many nuclei, you can get a chain reaction, which we're all familiar with. A neutron comes in, causes fission. In this cartoon, it produces 2 neutrons, which produce 2 more fissions, and so on. The public is now familiar with chain reactions through the virus as a chain reaction. But compared to a nuclear chain reaction, that's a negligible chain reaction. Doesn't do, the damage it does physically is negligible compared to a nuclear weapon. In a nuclear chain reaction, you can go through 80 generations of fission in 1 microsecond, which would fission 1 kilogram of material. And that fissioning gives an explosive power equal to about 15,000 tons of TNT. So the explosive power, the yield of nuclear weapons is measured by the equivalent weight of TNT that you would be required to make that explosive power. So a nuclear chain reaction is 15 million times more powerful than TNT. 1 pound of fissionable material is equivalent to 15 million pounds of TNT. But you need enough nuclei there to get the chain reaction. And how many nuclei do you need? You need a critical mass. And the critical mass is just determined by, it's just a neutron transport problem. That is, the neutrons produced by fission, the neutron rate, the rate of neutrons produced by fission has to be greater than the rate of neutrons that are lost from the system due to diffusion or absorption by other nuclei. So it's just a neutron transport problem. The critical mass can be reduced if the neutrons are reflected by from the boundaries of the bomb assembly, which they are. And the numbers come out that the critical mass for plutonium-239, which is a highly fissionable material, is about 5 kilograms, and for uranium-235, it's about 15 kilograms. So this explosive power was weaponized a long time ago, and the most simple and the first weapon is a gun-type fission weapon. It's very simple. You have 2 subcritical masses that are shown in blue. So on the left, you have a subcritical mass. On the right, a subcritical mass. And a chemical explosion forces the left one, like a bullet, to travel down the tube and merge onto the other blue mass of uranium. When the 2 merge, you get supercriticality, and you get an explosion. It's very simple, uses uranium. It's very inefficient. It burns up only about 1% of the uranium, so it's not efficient. It wouldn't work with plutonium because it's too slow, and most plutonium has some contamination with plutonium-240, which spontaneously fissions and causes the bomb to fizzle. But this was used, it's so simple, it was used without a test in 1945 over Hiroshima. But it's inefficient, so a more sophisticated weapon is an implosion-type weapon, which is more rapid, and you can use plutonium, which is more fissionable. And this is, in these cartoons, I've never designed a nuclear weapon, but these I can only speak by cartoons. You have a spherical assembly, and here you have a pit of plutonium that's forced to implode, and as it implodes, the mass becomes supercritical and you get the explosion. And the implosion is triggered by chemical explosions that surround the edge and are shaped in a way to cause an inwardly propagating shock wave. It pushes on a uranium shell, which pushes on a spacer, pushes on the plutonium, crushes it down. At a particular moment, a neutron source is triggered that starts the chain reaction. So it's more powerful, more efficient, but more complex. It's more efficient, and this was used in Nagasaki after 1 test in the desert in the United States. It's more efficient in Nagasaki. I think it burned up about 13% of the plutonium. But modern weapons introduce fusion reactions, which those in plasma physics we love. And the fusion reaction is the DT fusion reaction. A deuteron and a triton gives rise to an alpha particle and a neutron with about 1,000-fold amplification in kinetic energy. The tritium is not found in nature, and it's actually bred in the bomb, just like it would be in a fusion reactor. And it's bred by the neutrons bombarding the lithium, which then transmutates to produce a tritium, a triton. So you get the extra explosive power of fusion, and this is a 2-stage weapon. There's a primary on the left, which starts it off, which is much like what I showed you on the last slide. It's a little bit more sophisticated than I showed you, but it's mainly a fission bomb. It starts the explosion. And this fission bomb on the left generates a large amount of X-rays that fill this chamber with X-rays. The X-rays then bombard this spherical assembly, which again causes an inward implosion. And the implosion crushes down a lithium deuteride, which then turns into a hot plasma. And the deuterium is there, and the lithium is transmutated into tritium, well, through a transmutation. And you get a fusion bomb. So you get a primary and a secondary. It's much more powerful, and those are the modern bombs today. The yields from these bombs, the explosive energy is enormous. The largest conventional weapon, and conventional means a chemical weapon, is about 11 tons of TNT. The Hiroshima bomb was 15 kiloton TNT equivalent to about 1,500 of our largest conventional bombs. A typical warhead in the world today is maybe of order of 300 kilotons, which is about 20 Hiroshima bombs. The largest detonation ever made was in 1961. The Soviet Union over the ocean exploded a 50 megaton bomb, which blew out windows in buildings 600 miles away. So the yields are really incomprehensibly large. And what does a single bomb do? Well, this is well known for 70 years. This is very, very old material, the physical effects of a single bomb. But what's new really is that we're still suffering with them 70 years later. Roughly speaking, about half the bomb comes out in blast energy. The bomb generates a blast wave or a shock wave that carries about half the energy. About a third of the energy is thermal energy from the flash and heat. And about 15% is nuclear radiation, prompt gamma rays and neutrons, and then delayed radiation from decay. So this different forms by which the energy emanates can lead to fatalities a whole lot of different ways. The blast wave can do damage. Winds that are produced do damage. Burns, fire, and radiation. So there's lots of ways that you can be killed from a nuclear weapon. Here's a cartoon of a blast wave or a shock wave. They're the same. And here you can see there's a explosion above ground, and it generates spherically outgoing shock waves with steep shock fronts. Some of the shock waves reflect off of the ground and then merge on to the pre-existing ones and amplify the blast wave. And here's a cartoon of what it looks like versus distance. This is the overpressure, which is the pressure in the blast wave above atmospheric pressure. And you can see as time moves on, it decreases in amplitude, but you have a very steep shock front. And then you have a gradient in pressure that generates very strong winds. So this propagates outward. And what are the effects of a blast wave? If the overpressure is 5 pounds per square inch, it'll destroy residential buildings and generate 160 miles per hour winds, which is equal to that of our strongest hurricanes. If you have a 10 psi overpressure, it'll destroy basically all buildings, and you get 300 mile per hour winds, which don't occur naturally. This was measured, the effect was measured, for example, in this test in 1953 in Nevada. They exploded a small nuclear weapon, a 16 kiloton, and they had a wood frame building 3,500 feet away, 2/3 of a mile away from this nuclear explosion, and they photographed what happened. And you can see that initially the light from the explosion lights up the house. The thermal radiation arrives and starts to burn the paint, and then you can see that the house just gets blown apart, and this exposure is 2.3 seconds, so just 2/3 of a mile away, the small nuclear weapon just blows away the house. But modern day weapons are stronger. And let's take the case where you have one explosion of one 350 kiloton bomb, just as an example. This example exploded at 8,000 feet. The pressure goes down rapidly with radius. Distance from the bomb goes like 1 over distance cubed. But an average size bomb if the ground zero is here, up to a 2-mile radius away, the overpressure from the blast wave will be 10 psi or above. So up to 2 miles away, you have 100% fatalities, and all buildings are leveled, roughly speaking. Everything's annihilated. 3 miles away, you have 5 psi. It's estimated about half of the people will be killed. In addition, from the thermal radiation, 3rd-degree burns, the thermal radiation dies off more slowly, 1/r squared. So up to 4.5 miles away, you can get 3rd-degree burns. And if the 3rd-degree burn covers more than 1/4 of your skin, it's fatal. So nuclear weapons are not war-fighting weapons. It's a weapon of genocide. It just kills all adults and children within miles of the bomb. Plots like these are often shown. If you, here's a plot of that 350 kiloton warhead exploded in downtown New York, Manhattan, sort of actually close to where the 9/11 attack was, and that killed 3,000 people. But here you can see you'll get 3rd-degree burns out into New Jersey and Brooklyn and Queens and Staten Island. And in very rough numbers, it's estimated one bomb in New York City will kill about 1 million people, injure about 2 million people, so it'll basically destroy New York City. So just one bomb in Manhattan, it wouldn't be like 9/11, it would be the worst catastrophe ever to hit the US, probably. Well, there was a calibration in 1945 of these effects. The Hiroshima bomb exploded over Hiroshima, which, as I mentioned, is a small one, just 15 kilotons. It's a grim calibration. Over 100,000 fatalities, mainly from burns, falling debris. The winds knock down power lines, and the heat and so on causes fires. So you get fire storms, this continuous fire. So Hiroshima had a 4-square-mile firestorm, sort of pictured on the left. And on the right is a photograph of what used to be a city. And you can see it was just completely leveled for miles. This is the size of the plutonium pit for a 15-kiloton bomb. This was a uranium bomb that did Hiroshima. But if you did it with a plutonium pit, that amount of plutonium would destroy a city the size of Hiroshima in 1945. So this is some history. What about where are we today with nuclear weapons? Well, since that one bomb in Hiroshima, nuclear weapons have been mass-produced, and it's become a very big industry. And nuclear warheads or nuclear bombs are spread over 9 nations at the moment. And here on the horizontal axis, you can see the 9 nations that are nuclear weapon states. And on the vertical axis is the number of warheads, number of bombs held by each country. And you can see that Russia and the US have over 90% of the nuclear warheads. Summed over all 9 nations, there are over 9,000 nuclear warheads today. And in Russia and US, about almost 2,000 each in each country are deployed, that the warheads are mounted on delivery vehicles. About another 2,000 are in the active military stockpile, but stored in warehouses, ready to be uploaded if needed. About 2,000 each are ready to be retired. And then you can see that, from Israel up to China, there's like 100 to 300 weapons per country. And it seems negligible in this scale, but there's enough weapons outside the US and Russia to also pretty much end civilization. And North Korea here is the most recent entry with estimated about 30 or so nuclear weapons. So it's spread around the world. The weapons are spread across what's known as the nuclear triad, land, sea, and air. There are nuclear weapons in submarines right now prowling the oceans, and submarines are survivable. They cannot be detected, so it's kind of an invulnerable retaliatory force, and the weapons can be prompt. You can launch them and launch a ballistic missile, and it's going at Mach 20 or so toward your target. Bombers or aircraft carry nuclear weapons, and they're flexible. They can maneuver around, and they can also be recalled. If you send a bomber on a mission to drop a nuclear bomb and you change your mind or made a mistake, you can call it back. You can't do that with ballistic missiles. And finally, in land, there are intercontinental ballistic missiles, ICBMs. In the US, there are 400 stored in underground silos in the states and the West. The total world arsenal sums in very rough numbers to around several thousand megatons. These numbers don't mean much, but for comparison, the entire bombing of World War II, which killed 60 million people, was 3 megatons. We have about several thousand megatons, or we have several 100,000 Hiroshima bomb equivalents in explosive power in the world. So by the direct effects I mentioned, the bombs, through blast and fire, can kill billions of people if we were to use them. But it gets worse than that because there are indirect effects of multiple bombs, nonlinear effects that extend geographically and extend in time. One is fallout, where the dust that's brought up combines with the radioactive debris, and I'm not going to talk about that at all, it's well known. Another one is an indirect effect, almost silly to talk about, is a breakdown of infrastructure. We talk about hospitals being stressed in COVID. Well, clearly a nuclear bomb will eliminate your healthcare system along with eliminating the people. And it's hard to understand what it will do to the financial system, political system. Just one almost a stupid factoid. In the United States, total United States, there are about 2,000 burn beds. That is, the United States has capacity to treat about 2,000 burn victims. And clearly one bomb in one city can generate hundreds of thousands of burn victims. So victims would just die without any health care. But what I want to spend a few moments talking about is the effect of multiple nuclear weapons on the Earth's climate. This would be climate change, much more rapid and much more drastic than the climate change due to the greenhouse effect. And this has been called nuclear winter, and there's been recent research on this. And the physical effect is very simple. The climate is disrupted by the massive fires, the firestorms that are generated by nuclear weapons. If nuclear weapons detonate where there's flammable material, it causes massive fires that produces carbon particles or soot. The carbon soot or smoke is heated by the sun. It rises into the stratosphere, 60 to 30 miles above the Earth's surface. Once there, it spreads out, diffuses, or is blown around the Earth. And as in this artist's conception, the Earth becomes covered with a shroud of black smoke. It blocks out some solar radiation, so the result is that the temperature decreases and sunlight decreases. Now, climate scientists, not many, because this is not a funded area very much, it's not funded by the government at all, but climate scientists have used current climate models to model this effect. And they've done recent studies of a regional nuclear war. They took as a case study a war between India and Pakistan, two adversarial nuclear powers, where they each exploded 15 kiloton bombs. So they set off 100 small bombs against each other's cities. And this is just 0.1% of the world arsenal of nuclear weapons. It would generate about 16 million tons of carbon soot. And this is what it does to the temperature. Here's the globally average temperature from 1880 to the present. You can see the global warming. And then India-Pakistan has a war, and it decreases pretty instantaneously the temperature by about 1.25 degrees Celsius, and more, it's not uniform, more locally. So this would be the greatest climate change in recorded human history, and it recovers over 10 years. And what does this do? It causes crop production worldwide to decrease. Different crops decrease at different locales by amounts in the range of 10 or 20%. And some estimates, and I'll come to some more accuracy later, some estimates on this says that it would place about 2 billion people at risk of famine, because people already live on the edge. So if you decrease crop production, you can drive a large number of people into famine. So many more might be killed outside the war zone than within the war zone. This war would kill about 20 million people in India and Pakistan, but many more outside. So nuclear weapons target innocent bystanders and innocent nations. They don't just, the effects don't stay within the adversarial nations. But these climate scientists have more recently looked at the effects of a full-scale war between US and Russia. And here's their results from US and Russia. Here's the temperature globally averaged. Here's the global warming. And here's the India-Pakistan war. And here's a full-out US-Russia war. The globally average temperature drops about 7 degrees Celsius. And they looked at what this does to the caloric intake of the average person. And here's a plot of the globally average caloric intake in year 2 after the nuclear explosions. And on the vertical axis, it has the caloric intake per capita per year. And on the horizontal axis is the amount of smoke generated in teragrams. And here you can see this is the caloric intake on average today. And if on average people consume less, they're going to start losing weight. And here's the resting energy, just the energy you need, just the calorie consumption, just to keep yourself going without any motion. And if you have consumption less than that, you're probably going to die. And here is the India-Pakistan war. So the average caloric intake, and these different bars and different markings are different details of how people are consuming, whether people consume feedstock and so on. So the details aren't important for the level of detail I'm discussing right now. So India-Pakistan, you can see the average consumption drops seriously. A US-Russia war is in here, and you drop on average below your resting energy intake. So it can pretty much kill everybody by the climate change. And so a nuclear attack is also a suicide attack at this level. And really nobody understands this well. So people that control nuclear weapons don't understand the effects of the nuclear weapons that they're controlling. Now, there are some dangerous policies, or policies that many people consider to be dangerous policies. I'll mention a few of them. One is that there are weapons kept on hair trigger alert. And the definition of hair trigger alert is that they're ready to launch in just minutes, 5 to 10 minutes, of receiving a launch order. And right now, in Russia and the US, there are about 1,900 missiles that are on alert status in underground silos and in submarines. And so this is what leads one to say that at any moment, we're 10 minutes away from ending civilization if somebody decides to do it. And this is clearly prone to accident. I mean, anybody here who works with hardware knows that something like this in trigger alert, it's prone to accidents, vulnerable to hasty decision. In the United States, the president has the sole authority to launch nuclear weapons. The president can decide to launch a nuclear weapon and has no obligation to consult anybody. Nixon said to someone, I can pick up the phone now and in 10 minutes, 100 million people would be dead. And so there's no checks and balances written into our system whatsoever. A similar policy that's dangerous is that the US has the system primed to launch nuclear weapons on warning of an attack. It's called the launch on warning option. So imagine that Russia launches a weapon toward the US. It goes, I guess, hundreds of miles above the atmosphere, and it takes about 25 minutes to land in the US. So if one wanted to launch weapons before they landed and took out our own ICBMs, you'd have a very short time to do it. If you look at the time scale, imagine the Russians launch at T=0. Infrared detectors on satellites, take maybe a minute. They detect the rocket plume. A few minutes, they inform the military. The president's notified. A few minutes to assemble his advisors, so his right now. And considering the time it would take to transmit, the minutes to transmit the launch order, the president might have 5 minutes to be briefed, to have options explained, and to make a decision whether to launch nuclear weapons or not. If he decides to do so, some minutes it takes to receive the message, and at T=23 minutes, the missiles are fired, and then the Russian bombs land in the US 2 minutes later, unless it's a false alarm, and then the president would have hastily started a nuclear war by accident. So this is a very dangerous situation. I think self-evidently, no person has the capacity to decide whether to launch a nuclear war within minutes. And it's totally unnecessary because the submarines are invulnerable underwater. They can be used at any time. Another policy is the absence of a no first use policy. US and Russia both reserve the right to start a nuclear war. We have a policy that we reserve the right for first use, which is in opposition to the whole principle that nuclear weapons only exist to deter someone, and you would only use it to retaliate. Well, that's not our policy, and I'm not going to say more about it right now. Now, one might feel comfortable that we've gone 75 years without nuclear detonation, but we've been lucky, and there have been many, many known close calls, and many maybe close calls that we don't know about, but many known close calls, and I'm going to kind of break a good practice for giving talks. I'm going to read through the slide quickly to show you some false alarms that have occurred and are well documented and well known. In 1960, a US radar in Greenland reported that dozens of Soviet missiles are headed toward the US, and the US air defense was put on maximum alert. It turned out it wasn't real. The cause was radar, which was fooled by a moonrise over Norway. 1979, a US military computer detected 200 Soviet missiles headed toward the US. The ICBM crews, you know, the people that stay underground in the silos ready to launch the ICBMs, were put on high alert, and nuclear bombers were prepared for takeoff, and it was a mistake. It's actually not known what the mistake was, but somehow it seems the story is that a tape that was simulating an attack got loaded into a real operational computer, and it wasn't real. In 1980, the National Security Advisor Brzezinski was wakened up in the middle of the night by news that 200 submarine launch missiles from the Soviet Union were headed toward the US. Again, in this case, the ICBM crews actually opened the safe to retrieve the nuclear launch codes, and it was a defective computer chip. Going the other way, in 1983, a Soviet satellite detected 5 US missiles heading toward the Soviet Union, and it was just sunlight reflected from clouds. And in 1995, Russian radar detected a US submarine launch missile to strike in 15 minutes, and Russian nuclear forces put an alert, and President Yeltsin retrieved the nuclear launch codes. It was a US scientific rocket that was launched to study the aurora. So these were false alarms, and in all cases, what happened? Somebody judged or intuited that the alarm was false. In some cases, they disobeyed orders. A US officer should have notified the president but didn't. If the US officer notified the president would have thought, I have minutes to decide whether to retaliate, but that didn't happen. Now, going the other way, a Soviet officer was supposed to, from the signal on his radar, he should have recommended a retaliatory launch, and he didn't. He just figured it's not a point of high tension. The US would not attack us with 5 missiles, so he didn't order a retaliatory launch. And I think he was fired, and he's now, there's a movie about him. He was called The Man Who Saved the World. So we've been lucky. There are other kinds of close calls. There have been mishaps with warheads. In 1961, a nuclear bomb was accidentally dropped from an airplane over North Carolina. It didn't detonate. 1980, there was a chemical explosion in an ICBM silo that propelled a 9 megaton warhead 200 feet into a ditch. There's a whole book written about this. It didn't explode. In 2007, there were 6 missiles, nuclear missiles, were mistakenly flown from Louisiana to North Dakota by accident. In 2010, there was a gap in the control. There was a loss of control over 50 ICBMs in Wyoming for 1 hour. For 1 hour, we didn't have control over those ICBMs, and more. I won't even get into the Cuban Missile Crisis. Anyway, this led General Lee Butler, who had been head of the US Strategic Command that oversees nuclear weapons, to say that we escaped the Cold War without a nuclear holocaust by some combination of skill, luck, and divine intervention, and I suspect the latter in greatest proportion. So we've been lucky. Where are we now? So it's argued pretty broadly now that the nuclear world order is in crisis right now because of changes, both geopolitical and technological. And this was captured just metaphorically. You can take this for what it's worth, but metaphorically, the Bulletin of Atomic Scientists every year comes out with their doomsday clock. They've been doing this, I think, since 1945. How many seconds we are from midnight, where midnight is some big doom, for example, a nuclear war. And in 2020 and 21, they put it 100 seconds before midnight, which is the closest it's been throughout the, it hasn't been that close, according to this panel that makes this conclusion, since 1945. A bottom line of this is we are slipping into, we're now at the beginning of a new nuclear arms race. So let me indicate why things are dangerous right now. So the increasing nuclear dangers. Well, there's been a gradual proliferation of nuclear weapons. So now the world is not bipolar. It's not the US and Soviet Union only and two necessarily rational actors. There are 9 nations that have nuclear weapons. Corral them off, US, Russia, China, the UK, France, India, Pakistan, Israel, and North Korea. And they all have different tensions and rivalries and all sorts of things. So this whole system is more accident prone, less controllable, more scenarios for some conflict to escalate to a nuclear catastrophe. There are non-state actors, terrorists, and that's been spoken about a lot. If they get their hands on nuclear weapons, usable material, of which there's a lot floating around, that would be dangerous. This is an emerging threat of a cyber attack, and I think nobody understands this fully. Clearly, this is an emerging technology, but you can imagine what a cyber attack would do or could do. I mean, it could provide a false warning. What if we got a false warning that there was an attack? What would we do? It can maybe hide a real attack. It could interrupt the communication between a leader and his or her military. Worst case, maybe it can enable an unauthorized use of a nuclear bomb. So this is a very serious threat that makes control of the, I guess it makes accidents more likely to happen. There's been a fairly steady erosion of the arms control regime manifest through a termination of important treaties. And I'll come to these a little later. The Anti-Ballistic Missile Treaty that put a limit on countries' defenses, the US withdrew from it in 2002. So we have no limit now on the defenses that can be put up in Russia and the US. I'll come back to this. In 2018, we withdrew from the Iran nuclear deal. I won't be discussing it. We can discuss it in the discussion if you like, but we withdrew from that, which has brought Iran closer to becoming a nuclear weapon state. The US and Russia in 2019 withdrew from the Intermediate Nuclear Forces Treaty, which I'll come back to. In 2020, the two countries withdrew from the Open Skies Treaty, which allows about 30 countries to fly over other countries' territories and surveil them. So there's transparency of what's going on, and that treaty has collapsed. But maybe the most explicit indication of that we're going backwards is that we're now in a new nuclear arms race. The majority of nuclear weapon states are doubling down and beefing up, upgrading, modernizing, developing new nuclear weapons. This is most, at the largest scale, this is occurring in the 3 superpowers, Russia, the US, and China, but the UK is, I think, increasing the number of warheads by 40%. So there's a weapons modernization in several countries. In the United States, we're beginning a program to spend about $1.5 trillion over 30 years to replace everything, all the 400 new ICBMs, 10 new nuclear submarines, everything brand new, at a cost of $1.5 trillion, which would commit the US to nuclear weapons beefed up through to the end of the century. Similar in Russia and China also, although they were building up from a much, much, much smaller nuclear capacity. Countries are developing new weapons and new defenses. There's new low-yield nuclear weapons being developed, hypersonic nuclear weapons, which instead of going on a ballistic trajectory, can skirt along the Earth's atmosphere and maneuver and perhaps evade defenses. I think it's sort of technically doesn't add anything except in the arms race sense. It fuels arms races. So we're now at a new nuclear arms race. Now, well, another quotation. This has led William Perry, who's a former Secretary of Defense. He said today, and he made this quote in 2015, and this is what he said in 2015, and in the last 6 years, things have gotten progressively worse. He said the danger of some sort of nuclear catastrophe is greater than it was during the Cold War, and most people are blissfully unaware of this danger. Now, I know this sounds kind of bleak, and so what's needed? So what's needed is public pressure on governments to improve the situation, and they won't do it without public pressure. And governments can act to reduce the threat. This is a man-made threat. It's not like, climate change is man-made, but climate change is much more difficult because you need scientific solutions. It's much more difficult. This is just, all you got to do is disassemble the nuclear weapons. And governments have acted to reduce the threat. So I want to give some examples of excellent progress from the past to show that governments can act to make us safer from nuclear weapons. And the one is the cornerstone of the nuclear arms control regime, which is the Non-Proliferation Treaty. And it's more than non-proliferation, as you'll hear in a moment, which was signed in 1970 by all nations except 3. And then North Korea more recently withdrew. So almost all the nations of the world signed this treaty. And it's a deal. And there are 2 major parts to the deal. The first one, at the time of this deal, there were 5 nuclear weapon states: US, China, Russia, UK, and France. And all the non-nuclear weapon states, the majority of countries in the world, agreed not to develop nuclear weapons. They don't need them, they won't develop them. The other side of the deal is that the 5 nuclear weapon states agreed to work toward, and this is a quote, cessation of the nuclear arms race at an early date and to nuclear disarmament, getting rid of all nuclear weapons, which is the only safe, stable state. And this treaty has been partially successful and partially not successful. Here's one result. Over 50 years since it was signed, there's only been an expansion of nuclear weapon states from 5 to 9. So here you can see the number of nuclear weapon states over time, and it's climbed, and it's kind of saturated now. Here's North Korea, and it hasn't, back in the 40s, 50s, it was thought that by today we'd have dozens of nuclear weapon states. And thanks to the Non-Proliferation Treaty, or in parts to that, that's not the case, although it's still terrible. But it's also set a legal requirement on the nuclear weapon states to disarm. And that's not happening. As I showed, we're going in the opposite direction. In 1972, here's another good thing, US and Soviet Union signed the Anti-Ballistic Missile Treaty. It barred both countries from deploying or trying to deploy nationwide defenses, which would be impossible to do. Any defense can be easily overrun by decoys or more offense, but it prohibited a massive nationwide defense. It limited each country only to 100 missile interceptors. And the reason to do this is because it stabilizes things. If one country develops defense, another country will always do a worst case analysis and develop more offense, and it causes a nuclear arms race. So the Anti-Ballistic Missile Treaty was a terrific thing signed in 1972 by the heads of the 2 states. And look what happened to the number of warheads in the world. What's plotted here is the number of nuclear warheads, and you see it goes up to 70,000 over the decades. And here is the total number in the world, which is mainly by the Russia and the US. you can see this enormous buildup to at one point in the 80s, we had 70,000 nuclear weapons in the world. It'd kill us all many, many times over. But look what happened. Well, we signed the Intermediate Nuclear Forces Treaty, which eliminated all medium-range nuclear missiles in Europe and in the Soviet Union. So that started bringing it down. And then there were these strategic arms reduction treaties, one after the other, and it eliminated 85% or so of the nuclear weapons in the world. Fantastic progress by rational players in Russia and the US. However, we still have a civilization-ending amount remaining. That's the problem. But progress can be made. Another good thing, there's been almost no testing of any nuclear weapons since 1996. Before 1996, there were over 2,000 nuclear bombs detonated just to test them, underground in the atmosphere, underwater. Usually these are done where people live and don't have any consent over it, and it's called radiation sickness, where these have been detonated. In 1996, the Comprehensive Test Ban Treaty was ratified and signed by many countries, but not all. But it established a norm, a taboo against nuclear weapon testing. And since 1998, only North Korea has tested nuclear weapons, nobody else. And that cap on testing is a limit to the development of nuclear weapons. There's a fascinating thing is that there are treaties around the world that establish regions of the world to be nuclear weapon-free zones. And there are 6 treaties that cover these different regions of the world. You can just read it. And each region has a carefully drawn treaty that prohibits all countries in that region from manufacturing, developing, possessing nuclear weapons. And if you look at a map of the world, all of these countries in blue are nuclear weapon-free zones, that by treaty, no nuclear weapons, and that has held true. And if, all the countries in red are the 9 nuclear weapon states, and those that are in yellow are neither, like Canada. Okay? And you see the entire southern hemisphere has no nuclear weapons. Those countries concluded that they're safer without the nuclear weapons, although those people would be killed along with the rest of us if other countries had a nuclear war. So this was a great step. And the most recent thing is that there's been drawn up a treaty on the prohibition of nuclear weapons. You know, chemical weapons, biological weapons, landmines, cluster bombs are all prohibited from use by international treaty because they're inhumane. But the worst weapon of all, nuclear weapons, doesn't have such a treaty. However, in 2017, such a treaty was drawn up, and 122 countries voted in favor. You can see that's not all the world's countries. All the nuclear weapon states and all of NATO kind of just boycotted everything. And just voting for it doesn't bring it into force. By sort of self-definition, the treaty was brought into force when 50 nations ratified, and that happened in January of this year. So this is a new treaty. The organization that pushed for this got the Nobel Peace Prize in 2017. It's had no effect on the number of warheads. This treaty is opposed by the US and other nuclear weapon states, but it might head in the direction of setting a new norm. So this is the situation, and some of us believe that the physics community can play an influential role in this problem that we're not currently playing. We can play an influential role as advocates, more than any other sector maybe, or many other sectors in society. If physicists make a statement about some nuclear weapon policy, it carries more weight, whether it's justified or not, than if accountants make the same statement. And there's a pretty nice tradition of physicists acting as citizen scientists in this arena since the origins, and I'll just mention a few. In 1945, there was a Franck report. This is Franck of the Franck-Hertz experiment, which had 7 signers suggesting that the US not set off the bomb in Japan, but rather just demonstrate it. Don't use it first, just demonstrate it for the Japanese, and that should have the same effect as detonating it. In 1945, there was a Szilard petition. Leo Szilard led a petition with 70 signers from the Manhattan Project that argued against the use of nuclear weapons and warned of a nuclear arms race. In 1946, there was a committee established called the Emergency Committee of Atomic Scientists, with Einstein as its leader, so to speak. And Einstein wrote that we scientists recognize our inescapable responsibility to carry to our fellow citizens an understanding of the simple facts of atomic energy. In that day, that meant atomic weapons, and its implications for society. What do you say? In this lies our only security, our only hope. We believe that an informed citizenry will act for life and not for death. So this is Einstein got engaged in this problem, not only warning Roosevelt to develop it against the Nazis, but then warning of the danger of nuclear weapons once developed. In Germany, there was a manifesto in 1957. 18 German physicists, including Heisenberg, opposed nuclear weapons developments and said they would not participate in such development. And reportedly, that played a role in Germany never becoming a nuclear power. In 1958, there was a petition to end nuclear testing. In 1995, Hans Bethe, who was a key player in the Manhattan Project, he said in 1995, which is pretty recent in nuclear weapons terms during the modern era, Hans Bethe said, I call on all scientists in all countries to cease and desist from work creating, developing, improving, and manufacturing further nuclear weapons. That's Hans Bethe. So, with that kind of heritage, a few of us formed something called the Physicists Coalition for Nuclear Threat Reduction. It's sponsored by the APS. It's partnered with the APS Office of Government Affairs, so we have sort of a professional government office with us at the moment. We have some support from the Carnegie Corporation. It's a national thing, but it's kind of headquartered out of the Princeton program on science and global security. And we have two goals. One is to re-engage the physics community in this problem. And the second one, more important, is to advocate. So we're building a coalition, which is a national network of just physicists, not as experts. Certainly, I'm not an expert in this problem at all, but just as informed physicists who will be willing to advocate for steps to reduce the threat. It's called the Physicists Coalition, but it's open to all physical scientists. It's open to all people working in engineering science. It's not meant to be exclusive at all. But the thesis is that working in an organized, collective way, we can be influential, help them make things better. There are many ways to reduce this threat, even short of disarmament, which is the ultimate way. We could and should take warheads off of alert status. We should implement a no first use policy. We should abandon the launch and warning options. We should restart arms reduction discussions with Russia and many more. So it's often said that nuclear weapons cannot be uninvented. That's the common, people say that, what can you do once the knowledge is out? And it's often said that the genie cannot be put back in the bottle, and that's false. We can't uninvent the knowledge, but we can put the genie back in the bottle and make the world much, much more safe. So if you want to learn more about the coalition, I know the hour is very late, but if Carrie permits, those that are interested can remain and we can talk about it. Or you can get information or join at the Physicists Coalition, at the website, physicistcoalition.org. You can also join through this code. So I really encourage anybody who cares about this problem to join this coalition, and you can really leverage your opinion through collective effort. So just to close, there was an article in Physics Today in 2018 by Steve Fetter, Dick Garvin, and Frank von Hippel. And Fetter and von Hippel are part of the leadership of this effort, of this coalition. And they had an article, the title was Nuclear Weapons, but the subtitle that they wrote is that with the end of the Cold War, most physicists turned their attention away from the nuclear threat. It is now time for us to re-engage in the debate over how to reduce the dangers from nuclear weapons. And I think that's a good statement of the status. So with that, I'll end. Thank you. Okay.
Thank you, Stewart. Let's have some questions. Abdul?
Yes, I have a comment and a question. You don't have to answer the comment. So a politician, I dare say, Stewart politician, would listen to your talk and say, we can fix the global warming problem by strategically exploding few bombs here and
right.
there to bring the temperature
Right.
or lower it down. So
Yeah, right.
we'll have to count on that. My question was, is the plot you showed was the staircase showing the number of nuclear-powered countries as time goes on. There was a step down just before Korea. Was that
South Africa had 6 nuclear weapons. And I think it happened at the time when the apartheid regime fell, they decided to dismantle their 6 nuclear weapons and not become a nuclear weapon state.
So that's why it went down.
That went down, yeah. But there's an interesting plot. About 30 plus countries at one point had nuclear weapons development programs and then abandoned them because they thought they'd be safer without them. And they didn't actually get to the point of nuclear weapons, but they abandoned them. Yeah.
Yep.
So I noticed in your chart of nuclear weapons powers, it goes monotonically up and then it dips by one in 19.
Well, that's what Abdul just asked. And that dip was South Africa giving up its nuclear weapons voluntarily, deciding not to do it. Yeah, they had 6, I think, gun type. Yeah.
With the great success in reducing the proliferation, why is it that there is no progress in disarmament? The countries which had weapons got a whole lot more over the years, and that's not setting an example. And how do we get the politicians to set the example that's needed for others to not grow in future?
So I think you say that the nuclear weapon states are setting, if I got it right, the nuclear weapon states by saying that we need these weapons for our security, so we say are encouraging other weapons to do the same, opposite to the disarmament. Is that what you said?
Yeah, I was just saying that there's great progress in reducing the proliferation, but there is no progress at all in disarmament.
Absolutely.
And I think the onus falls on those who have weapons.
I agree 100%. There are 2 problems. One is is the fear of proliferation, but the bigger and the existing problem is the fact that 9 nations have these civilization-ending weapons that they really can't control and don't understand the use of. And you're quite right, the hypocrisy is pretty stunning. That a country can say, we need these weapons for our security, but you can't have them for your security. Yeah, and it's very damaging, and it's an obstacle to disarmament. I can only agree with you.
So you mentioned that the US and Russia don't have a no first use policy that's ratified. Are there nuclear weapon states that do have no first use policies?
Yes, China. China has, through its history, has had a philosophy of minimum deterrence. So they currently have 300 nuclear bombs, and which is about 7% of the number that the US and Russia each have. So they've had a minimal, I mean, still a lot, but a minimal deterrent. They didn't want to get into an arms race or search for parity with the US and Russia because they thought, with 300, we have enough to deter and prevent being attacked. And they have a no first use policy they've always had. And then the next question is, well, they could just be lying. You can't verify a no first use intention. So it's backed up by the nuclear posture that you take. So it's thought by all analysts that China has their warheads demated from their delivery vehicles. They have warheads here and the rockets here. And that, of course, they can mate them, but it takes some time to do it. So they're having a no first use policy and not having their weapons on a ready to launch posture go together. The US is the opposite. We say we reserve the right to launch first, and we have about 800 or 900 weapons that we keep on high alert to launch within minutes. So these declarations can increase or reduce tensions. And so actually the coalition, as a coalition position that we advocate for, believe the U.S. should adopt a no first use policy, and that would make us more secure and safe. Russia and China have a no first use policy with each other, but not with everybody else.
Thanks for a great talk. I'm curious to hear your thoughts on the interplay between nuclear power and weapons proliferation.
In respect to nuclear power? So nuclear power and nuclear weapons are two different things, one peaceful, one not. They share technology, so that's how they get linked. And let me just say for the coalition, we have no stance on nuclear power. It's not our topic. And so there are people in the coalition that think or could be against nuclear power or for nuclear power, totally different. So they're linked because of technology, and particularly, as you know, you can the fissile material you need to enrich, the techniques to enrich fissile material for a reactor can also be used for a bomb. So that's where they get linked. So if someone wants to develop low-enriched uranium for a reactor, you build centrifuges, you can run the centrifuges longer and make it highly enriched for a weapon. Or if you have a peaceful nuclear reactor, you can use it not just to generate energy, but you can use it to breed plutonium for a weapon. So that's the cause for concern. And so I think there's a broad opinion that the way to solve that is to put all the all the fissile fuel under international control, and don't have individual countries enrich their own fuel. So if you have international controls, then that would make it easier to decouple, to have nuclear power, to save us from climate change while not increasing drastically the risk of nuclear weapons. So they're different topics. Yeah.
Any other questions? I was going to make a comment. Do you know of this book, The Los Alamos Primer?
Yeah.
Serber had some affiliations with the UW, and for anyone who's interested in the basic physics of the nuclear weapon, it's a wonderful read. It's easy to read, and it goes through the diffusion equation and all the basic data that they had. It's a beautiful book.
I second that. Yeah, it's great. It's freshman level physics that does it all.
Exactly.
Okay, Bob.
Oh, one more question. Yep.
What do you say to the Edward Tellers of the world who like bombs?
So I can't speak to Edward Teller, but I think that's look. There is a nuclear weapons complex. Some my colleagues call it the exterminist complex. That is heavily vested in this. So it's, there's $50 billion a year, 40, 50 round numbers, spent on the nuclear weapons complex. You should check this. I think 2/3 of it goes to industry. So there's a huge complex of interest in this area. And it's very interesting to hear the messages that they receive. You attend some of the meetings and you see, they would think my talk is totally biased and the wrong message. And you can hear the message that they're given, and it's an opposite message. So that's a big challenge. It's I don't know what to say. It's a big challenge. What the coalition wants to do is, what we'd like to do actually, is open up a dialogue with the scientists that work in the nuclear weapons complex. That would be an interesting dialogue.
Related to that, with NIF having just basically replicated your second slide on a small scale, is this something we should be doing?
So I heard recently, when the NIF, in one of the seminars where the National Ignition Facility had some very nice results, generating a lot of gain, a lot of fusion energy from imploding a pellet. So yes, I would love to have a conversation about that, because in one of the colloquia, it was introduced by Mark Herman, who's one of the leaders there, and he said this supports stockpile stewardship and modernization. They use the word modernization, which I found very, very interesting. So I think NIF then I took from that, is being partly sold by supporting the modernization. And I would just love to have that discussion of how that does that and so on. Yeah, that is an intersection there for sure.
Well, thank you, Stewart. Let's thank him again.
So should we allow people to stay if they want to just chat about the coalition?
Absolutely. I'm
Okay.
assuming
So
that
let's
anybody
take
would
a,
like to stay and chat.
why don't we take a minute break and people can leave and anybody stays.